Let's get started. Welcome to the CSS seminar. This is not a regular seminar time, so the following seminar still will be held on at 4 o'clock in the afternoon. So today it's my pleasure to introduce our speaker, Professor Guang from Purdue University. So Professor Lin is currently associate professor at the Department of Mathematics in the School of Mechanical Engineering. And he is also a concurrent professor, associate professor at Department of Statistics. He is also the director of data science consulting service at Purdue University. Prior to this position, he was senior staff scientist at the Pacific Northwest National Lab. He got his PhD degree in climate math from Guang University back in 2007. And he got his master and bachelor degree from Peking University and Zhejiang University, respectively. Okay, so today he's going to talk about the uncertainty quantification and machine learning for learning the physics from the noisy data. So let's welcome our speaker.
Thank you. Okay. So can you make the light a little darker? No. I mean, turn off the. So let's get started. So today I'm going to talk about uncertainty quantification and machine learning. So this figure, is basically I try to, one of the working I figured out, so I will try to improve our prime model. The reason is because like our IPCC report says 20 years, our global temperature increased 5 degrees, right? So then we have to do a lot of things, reduce greenhouse gas, etc. But how much do we trust our models, right? Our model has a lot of uncertainties. So we have to improve our model predictive capabilities. So if you look at this one, this is what observation data of the Central American precipitations. And this is what the model predicts. You can see they are totally different, right? So how do you rely on a current model to make a 20 years prediction, right? It works hard. So that's why we try to work on using satellite data, try to calibrate the model to improve the model capabilities. So this is our calibrated model, okay? It's getting better, but still not perfect, right? So you can see it's very difficult to calculate the very complex models. So that's the motivation, right? So why we want to do uncertainty quantification? So the goal is we try to, using the data, try to improve our model predictive capabilities so that we can use that to make a new scientific discovery and make critical decisions. So what I mean is a critical decision. One example is, for example, we want to using a current model to make a hurricane forecast, for example, right? You think about like this is a trajectory of the hurricane, okay, forecast, but it's in hourly, okay, updating. So we rely on this forecast model so that we can make critical decisions on where we can evacuation of residency, okay, so to reduce the damage, okay, so using our limited budget, okay. So that's the critical decision needs, okay. This is rely on how we, using the data we have, try to update our model. So this is like data asymmetry comes in play here. This is another work I work on at the Department of Energy. So we try to reduce greenhouse gas. So that we try. One of the idea is to inject the CO2, right, to the subsurface. Okay, compress it to inject the subsurface. But however, there's a lot of uncertainty associated with the reservoir underneath, right? Because it's natural reservoir, right? The greenhouse could like emit from the reservoir if there's some leakage going on, right? So just as a quantification, if you look at this CO2 injection, then the CO2 can expand right, in the reservoir or propagate in time. Okay, so you want to know how this CO2 plume gonna propagate, all right, in the reservoir. So there's a lot of very complicated modeling and asymmetric quantification work there. This is the first picture I show you, right? I want to do this calibration of the climbing models. Okay, this is a regional climbing model called the wall. Okay, so there's we want to calibrate it, so we have identified the parameter we want to calibrate. So there's 5 parameters we want to calibrate. So this is the 5 parameters one. Because why we pick up this 5? Because this is related to the convection scheme, related to the precipitation. So we identify these 5 parameters. Then we need some data, right? The data will come from the observation, the satellite data. We take from satellite data, we use satellite data, try to calibrate the 5 parameters. This is what we does. And we do that, so it's a show you, although if we use the default parameter, it's away from the observation, but after calibration, you can see the red color represents the millimeter per day precipitations. Okay, so model over predicted precipitations. Okay, if you do the calibrate that 5 parameter, you tune them, then you can reduce the precipitations. Okay, it's getting better, right? So reduces the over prediction, but still not perfect. Do you know why it's not perfect? It's because model form uncertainty, called structural uncertainty, or you call it model uncertainty, right? So your model is wrong, okay? Doesn't matter how good you calibrate parameters, your model is wrong, you will never be able to get to the right answer. Exactly, okay? You can have a little bit, but not exactly. So that's the next question we want to ask later. So the next question I want to ask ourselves is how I can quantify this, what if my model is not perfect, right? Can I get the model right? So this is the next question I want to answer here is how I can do data-driven discovery of the model physical laws using the data, okay, to calibrate it, or to find the physical law directly from the data. So I don't need any knowledge. I just give me the data. I try to find the physical law for it, all right? But this physical law will be the symbolic, okay? Just like we learn in the textbook. Okay, so this is the goal. Right? This is really, we can gain knowledge by discovering from the data. I think this is what the real data science is about. Instead of just feeder regression. You don't learn anything. Just like you're driving using the GPS. The GPS asks you to turn right, asks you to turn left, but you never know why you turn right or why you turn left. Right? But sometimes it's good, but sometimes it gives you trouble. Just like last week I was driving in Chicago, I believe GPS gives me very good directions, but when I get into the downtown, all these high buildings, right, the GPS signal taking away, then I totally lost. The GPS is going to just like randomly give you the directions, right? But in that situation, like you're lost, right? So you don't know where the direction should go. So that's, I think, the data science can give us a better view. So the question is, can we use the observing data to discover physical laws? The goal is trying to enable the data-driven scientific discoveries. So this is our recent paper published at the Royal Society. So we try to develop a robust data-driven discovery, a new way to discover physical laws. So this is we want to automatically discover the physical law. This is our goal. Try to using the data, try to find the physical law behind it. So that's a reviewed history of Kepler. So you know Kepler, right? Everybody knows about him. He discovered the planetary motions, okay, by analyzing the observation data. Right? We will not be able to touch the planetary, right? So this is, he only used the telescope to observe all these motions, right? Then he discovered the physical law behind it, but it took him more than 20 years to discover it, right? So the goal is can we using the data and automatically using machine learning to discover it automatically. So that's our goal. So let's try to do something. This is the outline of this part of my talk. So first I'll give us a problem setup, then I'll give you some toy problem, okay? Then I will tell you what's the limitations. Most people are playing with toy versions, okay? So far, but I want to tell you the limitation. Then I will talk about the new method we developed and show some results. The problem setup is given a set of data, okay? We want to find the physical law. And we consider, we want to learn the differential equation that I want to be different from the statistics. Okay? If you look at statistics, what statistics does, you give the data, give you a regression. Okay? There's no differential equation involved. So they just give you a regression, but that's not physical law, right? All we learn is that Newton's law, all these things are differential equations. So that's different. So think about that. So if I want to learn dynamic systems, right, dy dx, y is the output, x is your input. I want to learn physical law represented by the f, x, y. Okay, that's called dynamic systems. So assume that I give you some x and y, okay, and then you can also have compute the derivatives. And then you want to find the expression of that. Okay, so let's start from simple one. We look at about this problem. So let's look at our problem first. So I want to learn a symptomatic form. I need some basis, right? So I pick up some basis, such as up to second order. So I do that. So I basically, this is my output y. I'll calculate the derivatives. This is dy dx, right? This is my right hand side, left hand side. So this is my basis, right? I sample n points, so I have n go matrix, okay, n by n. So this is my weight, and then this is my noise. So noise is because my data has some noise, okay? So I'm going to use that. So the unknown is W1 to W6. I want to compute, okay? So if I fix W1 to W6, and I'm done to solve this type problem, okay? This is very, very basic. So let's do that. So each data one line in the matrix. So assume if our physical law is dy dx equal to x squared, then I use an algorithm to find that the w is 0, 0, 1, 0, 0, then I'm finding the physical law. Okay, so that's as simple as that, right? So we can learn the physical law. So many physical terms has a few terms in the equation which suggests a sparse method can solve the problem. Right? So I can have tens of hundreds of bases. I want to pick a few of them to represent the real physics that can help me solve the problem. Right? So that's the motivation we want to use in the sparse algorithms. Let's look at the limitation. So a lot of people develop methods based on these assumptions. They read many papers. But let's look at what's the limitation behind it. So first, the limitation, you assume the left-hand side always write like dy dx. Okay? So nobody tell you it's always like that, right? It may not even have first order derivatives, right? Yeah, it may have time in the space, it can be much more complicated than that, right? Maybe a nonlinear function. So we can replace these second order derivatives, right? Or third order, maybe, right? So nobody tells you it's like this one. So we don't want to have these assumptions. So the term in the left must exist. In the other word, we must know an existing term in the equation given here. Right? So this is a limitation about this. Right? You must know the dy dx. You must know something on the left-hand side, so you move it there. Right? So think about if equation, this is so-called Laguerre differential equations, like this form, you will never be able to using that I just described to learn this. Right? So there's a lot of limitations on the type problem I just described. So I want to build a more general framework to learn to cover any physical laws. Can use just one expression to cover it. That's what my goal here. So that's motivated to develop a general method. So this method is following. So I present a general version. So assume I want to find a basis. That basis I need assumptions, right? This, of course, anything you do, you have assumptions, right? So my assumptions, this physical law have up to k of the derivatives. It's the first assumption. Second assumption is it has up to like d dimension. Okay, so this is my assumption. Okay, d dimension polynomials.
So basically, the dimension is the spatial dimension.
Not spatial dimension. It's because it's like a x to the d, right? Like x to the d. Okay. So I will show you what's it. Okay, so basically I need the d positive. So then I do tensor product. Tensor product. The d represents the polynomial. So then I do the tensor product. So let's give example. If d equal to 1, k equal to 1, this is my basis. 1 x, y, dy dx. Okay? So if my d equal to 2, then I will contain the second order term. I have x squared, xy, y squared, etc. Okay, so then can you go on? Okay? So you make these two assumptions. One is d, but the other is the k. Represent how many derivatives you want to contain in your physical law, how high the polynomial you want to achieve in your physical law. Okay, only these two assumptions. If you assume a d and k, you didn't learn about physical law, you increase that to d and k. Okay, until you're satisfied. retain your framework. So if you do that, okay, just pick up these basic physical laws. Then you say that you build a basis like that. You build a basic function f1 to the fn. Each one contains we just described the components, the y parent, yk, okay, into your basis set. Then you say, I want to learn a 0 equal to f times w. Okay? So any physical law can fit into this. Okay? There's no one exception. Okay, so you can always fit it like this. Okay? So we want to learn the f and the w. So the f is you're choosing your basis, the w is your weights you want to learn. Okay? So then I want to discretize, I want to do a sample first, right? I sample, I obtain n samples, then I compute this f basis. On these n samples, then I compute this f. Right? I use the capital F to represent the sample. Then I fit a sparse regression problem 0 equal to f times w plus epsilon. Okay, so the f is my basis samples, the w is my weights unknown plus epsilon. So this becomes a regression problem, right? So then I just need to find the w. Okay, so simple as that. So think about this. But however, I'm facing a fundamental mathematical difficulty is if I solve this first term, if we use the sparse regression directly, we will probably get w equal to 0. Okay, this is trivial solution. It's because this is a homogeneous solution, right? Homogeneous equation, right? Right hand side equal to 0. The 0 solution always the easiest solution you're going to get, but this is trivial, right? You don't want to have a trivial solution. So to avoid that trivial solution, right? What we have to do is we need to fix one of the weight component as 1 to prevent the trivial solution. So basically, is I assume one of the w is 1. Okay, so I move to the left, then I figure the rest. I get one candidate model, and then I select another one, w equal to 1. I move to the left, I get another candidate model. So I can get a bunch of candidate model. Then I select one of the best fitted data. I get the best fitting model. So this way I can get a bunch of candidate model and pick up the best. I will show you some examples how I do that. So I fix WG equal to 1. For example, I move the FG to the left. So basically I remove the WG because I let WG equal to 1. Right? So then I move to the left minus FG equal to the rest of the W. Right? I just need to find the rest of W. Then I find one more. Okay, so that's the example I want to show you. So this setup, okay, so since FG might not be in the equation, so we have to repeat this procedure for different terms. Okay, so I can get a bunch of different models. So we require a sparse regression algorithm to find the error bars, so that can select the best model. So this is set up. So the idea is we want to find a t equal to phi times w. The phi is the basis. I just changed the notation to be phi because normally we use phi as a basis representations. Then times the w plus epsilon. So the sparse algorithm, okay, we modeled we used the Bayesian framework so that we assume a certified RD zero mean Gaussian with a variance, okay, which may be setting the was, but we can confirm the data. Okay, so that's we use a sparse Bayesian algorithm to try to determine. There's a lot of advantage associated with that. I'll explain later. So now I'm getting to the statistics. I want to explain to you how I obtain the sparse representation of the coefficient W. Okay, if you give me a bunch of data, it could be noisy data, but how I can robustly get the physical law from the data using these sparse Bayesian regressions. So we assume this given the W and the variance of the noise. Okay, this is two things we want to calibrate. Okay, this is the data you give me. Okay, so I represent the likelihood function. This is likelihood as a Gaussian function. Okay, given the data t, okay, we want to find out the W and the data noise, the variance. So we assume it's a Gaussian distribution, the likelihood. So this is the exponential part. We want to minimize this t minus phi w here so that it fits to the data. This is what we do here. So assume the Gaussian prior over the weights. So we assume this Gaussian prior for the W, right? This is we want to find out the posterior distribution for the W. So we have to need a prior using we want to use the Bayesian formulations. We need a prime model, so we assume the Gaussian prime for the models. There's a parameter, the alpha j here, represent the variance of my prime. So I can assume for the gamma prime on the alpha, we will assume this alpha satisfies the gamma distributions. So this alpha is my variance, okay, for my Gaussian prime. So it is satisfies gamma distributions. This gamma distribution controlled by 4 different parameters. Okay, so that's 4 parameters. It's very simple. We just assume A, B, C, D equal to 0. Okay, so that's why you see this algorithm, I don't need to tune much parameters. That's different from the like a unit network, we have to tune a lot of parameters. So this is very robust, we don't need to tune many parameters here. So this is the gamma distribution for parameters. Then we have the Gaussian prime to determine this W, then we this relation is T. Okay, so this is the relation. So the following, we're going to talk about the prime over the unknown. So this is the Bayesian formula, right? Basically, it is the prime times the likelihood, okay, functions, giving you the posterior distributions. Okay, so if we assume uniform prime on this ABCD equal to 0, then we can obtain this posterior distribution equal to prime distributions, the likelihood functions times the Dirac functions. Okay. The Dirac function can be approximated as there's 2 parameters in the Dirac function that can be pre-computed. So this is just a basic the linear algebra operations. Eventually, it's going to give you the posterior distributions that's equal to, you can say it's a normal distribution. That normal distribution given you depends on the mean and then the covariance matrix. Okay, but these 2 you can compute all depend on the data. So you can say this is the covariance, this is the mean. Okay, all you can just using the data you get to compute the Gaussian distribution is mean and the covariance matrix. So you can approximate it. Okay, so this can give you using data to compute the posterior distribution for the weights and the data noise. So once you have that, so you can obtain the posterior distribution for the weights. Okay? But I have to tell you so how I can, so I only obtain the posterior for each weight, right? But you have to evaluate which model is better, right? So this is another level, right? So first I'll tell you all the weights, what's the posterior distribution is. Now I want to know the model. How I evaluate the model, right? I have to evaluate the defined error bar. So the error bar is for each weight, okay, the covariance, the variance divided by the mean square, I sum them up. I use this to define error bars. So this is basically say I want to obtain all the variation of each weight, right? I sum them up. That tells me how much I should trust this model, okay, using these error bar definitions. But using this error bar, it can tell me how much I should trust each model. So let's show you some examples. Okay. So this is dynamic systems dx1, dx2, okay, equal to this. Assume you don't know this model. Okay, I don't tell you this. I only give you t and the corresponding x1, x2. Okay, this is only the data I give you. Okay, I give you a bunch of time series data about x1, x2. That's it. Then the homework is to find the physical law like this. Okay, this is the homework we want to do here. Okay. So let's say I want to using 2 different methods to compare. One is the proposed algorithm using sparse spatial regression, and the other 2 methods are using so-called sequential stretch code in the square that called lasso. Okay, lasso is a very popular method in this field. You guys know already. So the idea is we want to learn something like a dx1, dx2 equal to fw1 and fw2. I want to learn the f, the w1, w2 here. So if you show this thing is a tractor problem, there's a solution like this. Okay, you have x1, x2, the state. Okay, if you want the state like this. So then I'm using, so basically you say I inject some noise, very small noise, 0.1. So this is using the threshold in the square. This is using our method. This is lasso. This is using our method. Okay. So you can see lasso and our method perform very well. The threshold in the square have some trajectory away from the solution. So the red color is the exact solution, the black color represents the different learning trajectory you get from different algorithms. So if they overlap, it means a good match. So if I increasing the noise, because I want the method to be robust. So increase the noise, you see, if I increase the noise to 0.2, you can say the search coding is getting worse, right? The lasso and our approach is pretty good. That increase it again, you can say 0.5, this search coding dynamic is getting even worse. Still, pretty good. So keep increasing. Noise to 1.0, you see what happened to this too? Getting thicker, right? Why you get thicker? Because of course you inject too much noise, right? You inject noise, you're learning the physics is of course will deviate from the exact a little bit, right? Because of the noise. But still, they follow the trajectory, okay? Then keep increasing noise to 2.0. You see what happened to the lasso? The lasso deviated from the true solutions, right? So our approach, you can say, also still getting thicker, but still around the exact solutions. Okay, this demonstrates the robustness of our proposed method. I keep increasing. You see, the 500 is very big noise. But you can say this is also getting these both two methods, the other method getting worse. This our method is still keep the rough picture of it, right? So this basically shows the robustness of this method. Okay, so this is the ODE dynamic systems. Now let's look at a more complicated one like Lagrange differential equation. That's what we never learned using the time model, right? Let's try to see what we can do in this one. So in this one, this is the basis, right? We pick up the basis. You see, it's more complicated. The basis set is larger, right? The larger basis, so this is the model. I told you I need to fix one term to be 1, right? See, I figure this one term to be 1, and then the rest, I take it the next term to be 1 on another model, right? I pick another one, and another model, I can learn a bunch of models, right? You can see, totally I have then the 14 different models that evaluate error bar, this gives me the error bar. The one model learns 0.004. I think the smallest one is 0.04. Right? I say that is the good candidate model. So how many models you can learn from this thing? You can say there's 3, 1, 2, and 3. So using the data, I can learn 3 candidate models. Okay? So why is 3? Let's look at why is 3. So look at, if you compare this one and this one, you'll find out actually it's just switch the sign. Right? It's basically just switch the sign. Okay? So basically they are the same model, right? Then you switch the sign, you will eventually get the same model. Okay, so basically it's one model, just change the sign, give you the machine thinks it's 2 different models. But then you can use it, right? It's very easy to recognize just one model. So it's good. This approach method can find the physical law for you. It's basically says that. So this is basically the same model. It's just this is a little bit different numbers compared to this one. Okay, so it's basically the same model. Okay, so now let's go to PD. So how about the PD models? Right? Can we do PD models? There's a lot of challenges associated with learning PD models. The first reason is because involving spatial derivatives and temporal derivatives. Right? It's more complicated. You have more variables, especially for the system. For example, for this one, shallow water equation. Everyone recognize that we have the H, right? U and V, right? Are the 3 variables, and you have spatial X and Y. You have Z. It's getting more complicated, right? So if you naive general basis will be huge, right? So that's adding complexity to the machine learning. So that's the difficulty part I want to emphasize here. So this shallow water equations we want to learn here. So total we have H, U, and V, and the G's represent gravity. So here we want to assume the flow density is constant. We want to learn the physical models. So I generate some data. So using shallow water models, so generate data. So at different times. So we want to learn, okay, using the H, U, and V, okay, to learn, want to learn something like related to partial H, partial T terms. So that's the interesting thing we want to learn here. So if you just naive to search the basis, right, the combination will be huge. The possible basis will be huge. Because like my training is in like mechanical engineering, right? So we know something about the dimensional analysis. I think you guys from the engineering background you will know, right? So we learn something. If you learn fluid mechanics in that course, because I'm teaching fluid mechanics. So in the course I'm teaching students about dimensional analysis, right? The dimensional analysis tells you you cannot put arbitrary basis into your equations, right? It has to satisfy the dimensional analysis, right? So basically says the unit, if I want to learn something about partial h, partial t, right? The h is meter, right? The t is time, right? So this term will be the meter per time, right? So all your possible bases have to be meter per time, right? It cannot be anything, right? So the basis satisfied meter per time, that's not that many, right? It's only that few. So you doing that, you greatly reduce the possible bases to just a handful of them instead of thousands of them, right? So we do that, it can help us reduce the basis to add some engineering knowledge into that on the selection of the basis. So if we do that, you will see the possible basis, there's only that few of them. So then we want to learn the partial h, partial t, and the partial u, partial v, partial t here. Then eventually you will learn a physical law like this by using the shallow water data. So this represents the mean, and this represents the standard deviations, okay? So if you look at the standard deviation, it's like 10 to the minus 3 smaller than the mean. That means this is a good approximation. You find a pretty good approximation of the physical law. So what if you learn a physical law give you huge standard deviation compared to the mean? That means the physical law learned are not good, okay? That if this happened to you, there's two ways you can do. One is collect more data. Your data may be not good enough, right? The other way is you need to increase your dimensions. So what I mean is you may increase your derivatives, right? You may have to go to higher order derivatives, right? Or you go to higher order polynomials to fit the model, right? So that's but the good thing about this is very informative, right? Give you a lot of information. It's not like a neural network or something. You fit the model, okay? You find some black box. Good or bad, that's it, they give to you, right? You trust it or not, you use it, right? It doesn't give you the feedback. It tells you how much you should trust this model. Do you need more data? Do you need to expand this model a little bit, right? It also gives you symbolic form, right? It's not like the neural network give you a black box, right? So why the physical law is better? Because this one, you can use different initial and different bounding conditions to solve it, right? This is still giving you the physical law, right? The physical law will be valid in, doesn't matter in here, in the other place, it's just about the physical law. I think this is more universal, it's more useful, right? I think that more useful for the human being. So this is the shallow water equations, right? This is the mean plus or minus the standard deviations. Let's move on about this is shallow water equation exact. If we compare to this one, it's very close. Okay, so now let's move on to the Navier-Stokes equations. Okay, so why Navier-Stokes is more difficult? Because Navier-Stokes is nonlinear, right? You have a nonlinear term here, right? It's more difficult, more challenge, right? It's also a system equation, it's nonlinear, turbulence, everything hiding in here, right? So let's look at whether we can learn the Navier-Stokes. So Navier-Stokes, I also pick up a more complicated form. Instead of using the stream function vorticity formulation, that's much simpler. But I pick up the more difficult one, represented by the UV and the pressure representations. Okay, I use a more difficult representation. I'll show you. So I use a needle-driven flow to generate the data. So I use that data, then try to learn something. So this is the Navier-Stokes equations I want to learn. So I choose the basis using dimensional analysis, the same trick I will explain to you. So this is what I learned, okay? So I learned this is standard deviation, this is the coefficient, okay? So it's still very close to the Navier-Stokes exactly, very close, 10 to the minus 3 errors, okay? So this is not the main thing I want to present to you. It's more interesting I discovered when I try to learn the physical law, okay, in the Navier-Stokes. Because Navier-Stokes really is the holy grail about the physics, right? Let's look at the thing I learned. So I asked my student, right? He tried to discover the error bars, right? He told me he found a bunch of error bars equal to 0, okay? So he had 1, 2, 3, 4, okay? He told me he found 4 error bars 0, okay? It's very interesting. I said, whoa, we want to find something new, right? Let's look at what's new he learned, right? The first thing he learned is that u partial x plus u partial v partial y equal to 0, right? So that's common u term, right? If I take the u term out, what I got the u partial x plus partial v partial y equal to 0. What's that? It's mass conservation. Okay? So this basically, my algorithm can automatically discover the mass conservation for you. You will never be able to use this dynamic system stuff to the mass conservation. So this basically tell you, even you don't know anything about the mass conservation, right? You use this method, you throw it in the data will find the mass conservation for you automatically. The same thing, you can learn the moment conservation for you as well. So this good thing is because this approach can help you find some invariant measure in your data automatically, even you don't have any prior knowledge about your data, satisfy these conservations. I think this is very useful for you to discover some invariant measure because this is the physics really behind the data, right? We don't want to spend a lot of time to find it if the machine can help find it automatically for you. I think it's very important. And that's what other machine learning algorithm cannot discover. Think about your network will not be able to find the mass conservation for you because you never satisfy mass conservation. Okay, so this the first part of my talk I want to cover is our method does not need to know much about the form of the equation in advance. You can find the equation for you. And the method does not require the data come from the same initial condition and the bounding condition. So this is what I want to emphasize here is that I can collect, if I want to study the climate model for the Earth, I can collect data from Notre Dame, right, from Europe, from China, from India, from any different places, right? I don't care because it satisfies the same climate models, right? So I find the climate model, it also can use for different area of the Earth, right? So it's more universal, also it's more important. But also flexible when you collect the data, right? So I think that's the flexibility on the side. So our method can find the invariant formulation automatically, and also has better sparsity and more robust compared to other methods. And our method can give you a confidence interval for each parameter, and the whole equation can give you the error bar for that. So you can evaluate which model is better than the others. Okay, so that's the merits. So let's move on to the next part. Is what if I want to do something? Okay, on the predicting the arbitrary PDE solutions. So think about that. Right now, you guys want to solve a PDE, numerical PDE, guys, right? You want to solve a numerical PDE, you need a fundamental solver to solve it, right? So what do you think about in the next generation? I have a website, okay? I have an app, so you just using your hand, draw a geometry you want to solve, then you select the equation you want to solve, then click, then my neural network will come into play, find the solution for you. What if that happens, right? So today I'm going to present an example. I want to solve an elliptic equation, but heterogeneous, okay? And I want to solve the solution for you. So this is a paper just recently accepted in the GCP. We're using the fast convolution encoder-decoder neural network to quantify the uncertainty and for the heterogeneous elliptical partial differential equation on the different domains. Okay? So this I want to show you what we do here. So this is neural network. Okay, so we have input and output. So output is the solution of the PDEs. So we're using the neural network. So we have the input parameters. We have some hidden layers. Output predict the solutions. Okay, given the hidden layers. So if basically the idea is to do neural network, people want to do the optimization work. Okay, you do optimization. You basically want to define some loss functions. Right? The loss function, there's several different ways to define the loss function. One of the ways is to define using like an L2 norm. Okay, you want to do your prediction minus your observation. You want to L2 norm, minimize that. This is one of them. The other one you can do cross entropy. Okay, this is an information theory. You want to say how much information you gain. Okay, here. Or you can define hinge loss, this hinge loss definition here. So we use so-called encoder-decoder network. Okay. The autoencoder is following. So you have an encoder, this is the encoder. So you have the high dimension input, the encoder to a lower dimension. Okay, but it's nonlinear. Okay, it's not like POD. Okay, it's nonlinear encoder. Then you have decoder. You can decode to recover to the same representation of the input. Okay, so it has a very wide application. Think about like data compression, right? If you give a high dimensional image, I can use this one to compress it to a very small image. I transfer to another place and I decompress it. Okay, so that's a lot of. Also, this one we can use this one for the feature extractions. Your high dimensional data, you use an encoder can find out the nonlinear critical features, right? And then using that, you reduce the dimension, right? You can do model reduction using this one too. Okay, so it's kind of all kinds of application can be used here. This is called encoder-decoder models. So this talk about the convolutions, right? This convolution neural network. So convolution is you first do linear regression, then you basically put into the red loop, okay? Framework. So then we talk about the convolution layer. Basically, it's a matrix vector multiplications. So we do that. Then this is the convolution transport layers. It's basically multiplication matrix form. So because we are computational mathematicians, right, we want to speed up neural network. So we say what we can contribute here, right? So what we can contribute to using the scalable algorithm to speed up the convolution neural network. So one way is to you look at the computational complexity of a normal convolution layer. This is the computational cost. Okay? Depends on the input channel counts and the output channel counts and the kernel filter size and this total computational complexity. But however, it has some matrix structure we can take advantage of. Right? This is our computational guys normally good at. Right? So if you look at the matrix, right, we can use circular CAN to reduce the computational cost by leveraging using the so-called block circular matrix. Right? So we can apply this FFT and IFT to speed up the computation and reduce the computational cost. You can say you can greatly reduce the computational cost for these computations. So now let's look at these examples we want to learn. So think about this heterogeneous elliptic equations. So the idea is you give me an image of A, an image of X, give me arbitrary geometries, I predict the solution of U for you. I think it's generic enough for the individual set, right? You give me a heterogeneous image A heterogeneous image of F, I find a heterogeneous geometry you want to define, I find a solution. Okay? But of course, the problem has to be very close. It can give me any of A. It can give me negative A, for example, with one over. Okay? So this A has to be bigger than lambda, the lambda has to be bigger than 0. Okay? So this is we are posing some of the problem to satisfy. If we satisfy that, we can do something. The same thing, I have to define the cost function. Okay? This cost function is this is the internal observation point satisfied inside your geometry. This is the boundary condition you want to satisfy. Okay? So basically, I want to matching the internal part. I want to matching the boundary condition. Okay. So this is I use this is like a Lagrange multiplier. I use a lambda. Okay. To couple these two. Then I discretize the internal point and the boundary point. Okay. So this the loss functions. We want to minimize the cost functions. Then I have to train my model to arbitrary geometry. So these are arbitrary geometries. Right? I can generate arbitrary geometry to train my model. So I have to train my model with different F, source term different A. Okay, I have to train my model. So I have to generate a different kind of A and F to train my model. So this is prediction. Okay, we get so the right hand side is true, the left hand side is numerical predictions. Okay, about the geometries. So you can see it's not exactly the same, a little bit different, right? So you can see the neural network predictions are sometimes not as smooth as the exact solutions. Right? The reason is neural network they don't know the solution has to be smooth, right? They just train using your finite discretized solution to train the predicted solutions. Okay, so that's the prediction. So this is another solution. This is true. This is predictions. Okay. So this is the same thing. Okay, this is, you can say pretty much the same, except that the peak a little bit. This is not smooth. This is smooth. Okay, okay. So this true solution examples. Okay. So far I already discussed what we can do on predicting the such like whatever finite element can do, I can do. Right? Basically, I want to see that, and whatever finite element can predict, I can use neural network to do the similar things. So the next question I may say, what if a finite element cannot do? We can, right? So the next question I want to answer is, what if I know one thing the finite element cannot do is material fractures, the fraction mechanics, right? It's one of the difficulty because it's a non-local, right? So want to do something. So this is another paper. Where we develop a new neural network, pairing net, okay, that's able to, using the deep neural network to predict the crack patterns. So we submitted this paper to the Journal of Aerodynamics and the Non-Local Modeling. So we just got a review back, and the review back, they were saying this is the first work on predicting using neural network to predict the crack formations. So they like it pretty much. So let's look at what we can do here. So why we want to do these studies? So you look at this. So think about like our roof, right? If the here come down, generate cracks, and then our cell phone fall down on the floor, right? Sometimes the glass will be generate fractures, right? And also it has in the civil engineering, the bridge crack, all these things, has a very lot of application. I think civil people will like that, and mechanical people will like that too. Like the thermoelectric power plant, windmills, and also the power plants, nuclear power plants, all that. So why FEM cannot do that? It's because the FEM is local dynamics, right? It's not about non-local. So today we're going to talk about using the paradynamic models. The paradynamic is non-local extension of the classical continuum mechanics, so that it can model the fractures. Okay. So we want to using that. But however, there's a drawback always, right? The drawback is the paradigm is slow. Right? It takes a long time to get results. So that's why what we do is using the neural network to predict the solutions. So let's look at the problem setup. I have two setup of the problem. One setup is the inverse problem. Okay, so let's look at this picture. Okay, you think about everybody watching the movie, like the TV series CSI, criminal scene investigations, right? You think about this criminal scene. One criminal using a machine gun hit the wall, right? Generate a bunch of holes, and then the criminal investigator come in to take a picture, and they want to go back to investigate. So which criminal, using which kind of gun, what's the size of the bullet, using from which angle he's shooting the bullet, right? And they want to identify on that. Okay? So this is an inverse problem. Okay? So basically, I want to using this image, try to invert about the bullet size, bullet velocity, bullet shooting angle, all that. This is the inverse problem. And then the forward setting is think about you give me, you tell me about the bullet size, the bullet velocity angle. I want to predict how the crack is going to fall. In another way, is to think about you have cell phone, you throw down on the floor, I will tell you how the crack is going to fall on your cell phone. Okay, something like that. So let's look at how we can do that. So we use a benchmark problem. Have you guys do the fly disc problem? The fly disc, shooting a fly disc. So you think about you have a fly disc, you throw it, then you use a gun to shooting that fly disc, and the disc will break, right? So basically, we want to predict how the crack can form on the flying disc. So this is a problem set up. So think about this a fly disc. Okay, we're gonna shooting on any location of the red spot. Okay, I want to predict how the crack is going to form. I'm going to vary the shooting location on the disk. So I generated 100 hitting points. So my training is and then give me a new hitting location. I want to tell you how this fracture is going to generate. So this is fracture mechanics. So let's do that. So basically, it's this is a hitting location x, y. So that's also two inputs x, y. Okay. I give you an image of the crack. Okay. So this is the formations. And so our training error is about 0.06. This testing error is about 0.01. So let's look at so this left is using the DNS paradigmatic simulations. On the right, using the neural network. Okay, on the crack formations. So you can see, first of all, from the large picture, they pretty much close. Okay. And if you want to see the differences, the neural network is more regularized, okay? And also, it can capture the main fracture pretty well, right? All these main fractures. And then if you look at some, like this one, this is a small fracture on here, right? It's not exactly, right? The neural network predictor will go smooth a little bit, right? The reason is because the neural network, right? Think about this problem is strongly nonlinear. It got fracture, right? The hitting location of something you deviate from the 10 to minus 3, a little bit different. The small crack will be very different. Okay, so very sensitive to the shooting locations. Okay, So that's why when you use a neural network to predict all these small cracks will be smeared a little bit. But however, if you look at the speed up, right? If using the neural network it's like speed up like 10 to the 3, okay, seconds, okay, level on the predictions. So very fast predictions, and you can get it. So now I want to do even more difficult problem. What if I change the bullet size, I change the bullet velocity, I change the hitting locations, okay? So I train the data set, okay? So I have 3 variable I can vary, I want to predict. But of course, there's no free lunch, right? I have to change more data. Before I only need 1,000 data, right now I need 15,000 data. So using that data set, we can, to predict about this paradigmic solution, this is the prediction solution, you can see, okay, we can still capture the main fracture pretty well. Away from that, you can see it's getting blurred, right? Okay, so that's the image we can see here. And so you can see this is solutions, okay, at different hitting locations. Okay, so that's one of them. And also, you can see that, so you can pretty much match this one pretty well. Okay, on this one, on small fractures, is a little bit small there too. So now I'm going to look at the inverse problem. So the inverse problem I want to do is, I want to inverse, you give me an image of like this, I want to invert about the bullet size, bullet velocity, bullet shooting angle, and the bullet hitting locations. Okay, I want to inverse 4 variables by giving an image. So this is what I want to do here. So you can see I generate the training data set, okay, about 7,200 training data set, 1,200 about the testing data set. I simplify the problem into a classification problem to 8 different modes. Okay, so basically I want to find out which mode they belong to from the 8 possible modes. So I do that, basically give me an image, right? I want to, using the neural network, convolutional neural network, to identify the 8 classification problems. So if I do that, I can obtain a success rate of 95.6% on the classification to the right mode. So you can see this is the training input numbers. So the blue line is training curve. This red line is the validation curve. Okay, so you can see it's pretty good. It demonstrates not overfitting of models. So if you can see that we can predict the modes with the training error only about 0.06 and the test error only about 0.04. Okay, so that's basically show pretty good predictions on the classification. So here's a summary. So basically today I present to you about the UQ and machine learning can help us get insight to from the data and provide error bar on the machine learning predict results. Okay? I think it's very important on the machine learning to do some UQ because you can know how much to trust the machine learning results. Also, we provide a robust Bayesian learning algorithm that can learn physical law from the noisy data without much assumptions. And then this algorithm I represent generate error bar for your learning differential equations, which can select the best model. Also, I present the deep learning can be applied for scientific computing, such as learning PD, and also material failures and material fractures. Okay, thanks for your attention.
Thanks, Professor Lin. And I think we have 5 or 6 minutes to take any questions. So, any questions for Professor Lin?
So one place where this could be very valuable, especially because you straddle math and engineering, would be in DNS and LES models of turbulence. Because in a sense, we know what the coefficients are and how they're structured, but we just don't know where which coefficient needs to perk up in which geometry in order to kind of have a fully trained DNS or LES model. DNS, yes. DNS means it's direct simulation, but you can use a sequence of DNS simulations to actually train or get a more informed LES model from machine learning.
Yes,
That would be potentially very useful.
Yeah, this is one of the things I'm working on. I try to work on the super resolutions. So you give me, I try to train my model so that you give me a LES model, I try to enhance the resolution to obtain DNS-like resolutions. So that's what we try to use machine learning to do something like that.
May I ask one more question?
Yeah.
The other place where this could be very useful would be in Markovian processes. For example, if you take medicine, then there's a certain time over which your body forgets that you've ingested medicine. That's maybe half a day or a day, and then so in a sense, there are systems which have memory, and those systems are not representable as derivatives.
Yes.
They have integrals in them.
Yes.
Have you thought about how that can be incorporated?
Yeah, I think that's
Integral differential
integral differential equations. Yeah, I think that will be something. Yeah, we haven't done that yet, but I think it will be useful. It's about right? Yeah.
Any other questions?
Yeah, I'll read that. So one of the nice things about what you were talking about was that.
So a lot of the stuff that you've been talking about has been under very structured systems. So like you were using it for the Navier SOAPs, which we kind of already have an idea about. Do you have any idea how the Bayesian machine learning might be used in systems that maybe aren't as structured, that are a little bit more chaotic?
Yeah, I think the difficulty coming to doing the chaos system is to try to how do you guys going to compute the derivative information? Because in your chaotic system, you compute the derivatives will be very noisy, right? Because try to learn the PDE solution, you run the derivative information, right? If you have derivative information, that's like 10 to 3 errors in your derivatives, right? You will never be able to learn physical alright. So that's why you have to use some special techniques to try to compute the derivative. So there's a lot of technique you can do, try to compute the derivatives, reducing the noise when you compute the derivatives. Yeah. So yeah, that's some challenge. Definitely some challenge on doing the chaotic system. Yes.
Thank you, Professor. I was curious about your learning the physical law model. So if you have a discontinuity in your data, like you get the data from the double Mach simulation or some other equation with similar discontinuous solution, can you also learn the model as stable as it is currently? Thank you.
I think the answer will be similar things for you, right? I think the challenge for the discontinuity problem, right, like shock, right? The same thing about how to compute the derivatives, right? Will be same thing. You think about if there were discontinuities, right? So depends on where you compute the derivative. On the left side, right side is the central, right? You're gonna calculate the different derivatives, right? So of course, so the trick is what if you use a Vino method, for example, right? Use a Vino method to compute the derivatives, right? You identify where the slope is, and compute the derivative, how the derivatives, right? That way you still can compute the derivative information even there's a shock, right? But still, there's still a way to compute the right derivatives. Then once you learn the right derivatives, you can use the same problem to do the same thing. Yeah, it's still doable. Yeah.
Regarding to the derivative, I think you put noise into the data. So
Yeah.
would that affect your calculation of the
Of course,
derivative?
yeah.
So
You
how-
inject noise, of course, you're
Yeah.
gonna learn something.
I assume that the noise level, so how much noise you can handle by using current method?
So again, right, so this method good is about estimation, right? So it's gonna tell you error bar, right? So even you inject a lot of noise, what you gain, you can look at your error, right? You look at your standard deviation errors, right? If the error is big, you basically say, oh, there's no free lunch, right? If your data is garbage, you learn it's garbage, right? You are never learn the traffic from garbage, right? You're still gonna learn garbage. So, but the Bayesian method gonna tell you it's garbage. You go back and find a better experiments to do a better experiment, right? To get a better data, right? So I think at least give you information, tell you it's garbage. But if you using just neural network, you train it, you find the garbage, then right, you just use the garbage, right? I think at least this will tell you more information.
Okay, I have another question. Is So what if the data is generated from the parameter dependent system? For example, you have the data from the same PDE but with the different boundary condition, different different boundary condition and different PDE parameters. How can you use that kind of data to discover the PDE one?
So this physical law does not depend on the boundary conditions, right? I think you talk about so this one does not care about initial condition boundary conditions, right? So it doesn't matter. But you said that if there's a Reynolds number 1, you have some data, use Reynolds number 2 to generate another data. Is that something you want to?
Yeah, something like that.
You want to mix them?
Yes.
If you separate them, then you can do the same thing, right? If you mix them, it will be you have to tell me your Reynolds number is changing. Then I treat the Reynolds number as a parameter. Then I do that. I add into the learning process. I think that is also doable, right? I think it's doable for that. I just added Reynolds number as one of the very parameters, right? So I add it to the learning process. Yeah. So it's doable.
Okay, thank you.
One more question.
Yeah.
Is there for the Bayesian stuff that you're doing, like a toolkit, publicly available toolkit where you just put in the data and it kind of?
Yeah, you can play with it. You send it in your code. Okay, you can play with it. Yeah, no problem.
So it's relatively easy to code.
That depends on, of course, you have some statistical training a little bit. Right? You have to know a little bit of statistical training about the maximum likelihood, for example, Bayesian theorem. You need some a little bit of knowledge, but basic stuff. Yeah.
Okay, thanks, Professor Ling again.